Let's move on to the second half of this last calculus unit where we look at derivatives of exponential functions. Before we can do that, there's a few things I need to remind you about. I need to remind you about, firstly, what is Euler's number, which is represented with this lowercase e. And notice that it's equal to this non-terminating, non-repeating number, this 2.71828182845, so on number. It's an irrational number, which means it's a number that cannot be represented as a fraction, but it's so useful, just like how pi is an irrational number that's very useful, that we come up with a symbol so that we can use it very often in mathematics. And hopefully in your last course, you did an example with compound interest and looked at how if the compounding periods approaches infinity, you end up coming up with this irrational number. Let me just show you that quickly in Desmos. So that function 1 plus 1 over n to the power of n, as we let the number of compounding periods approach infinity, if we look at the value of this function, notice that it starts approaching this value of e that you see here. It starts approaching that 2.71828 so on number. And the reason why I needed to remind you about this is because when we differentiate exponential functions, we're going to be using something called the natural logarithm quite often. So if we have log base e of x, remember e is just this irrational number that you see there, we call that the natural logarithm. And this logarithm, where the base is e, is used so often that we have a symbol for it so that we don't have to write the base. And that symbol are the letters ln. So instead of writing log, we write ln of x. So if you see ln of x, well, think of the letters L and N because of logarithm, natural, standing for natural logarithm. We know that it's a log where the base of that log is e. So log base e of x is equal to ln of x. They mean the same thing. Many natural occurring phenomena can be modeled using base e exponential and logarithmic functions. And we'll do a few examples of those in this lesson. And our last bullet point here, log base e of e. Well, we would never write it like that. Log base e is the natural logarithm, so we'd write it as ln of e. That would be equal to 1. Because if you think about it, log base e of e, that means what exponent goes on e to get e? Well, of course, that would be 1. So ln of e is 1. And now let me remind you about what the graph of e to the x and ln x looks like. This should be familiar from your last course, so I'll quickly go over this with you, but it'll be a good reminder. E to the x is an exponential function. The base of the power is e, which is that 2.718 number. If I wanted to know what the graph of this looks like, well, I know exponential functions have horizontal asymptotes at y equals 0. And I'm going to pick some points on this function to get a good shape of it. So I'll pick the points that have x values of -1, 0, and 1, plug those into my equation to solve for y. So I'll have to evaluate e to the -1. So make sure you can find Euler's number on your calculator. It's the lowercase e. So e to the power of -1. That's about 0.37. And then e to the 0 is equal to 1. Any base to the exponent of 0 is 1. And then e to the 1, well, that's just e, which I know is about 2.72. So if I plot these points, and I draw in the horizontal asymptote, I can do a rough sketch of the graph of e to the x. And this is a continuous function, so make sure you show that with the arrows on either end, and I'll label this my e to the x function. Okay, now let me graph the function ln x. And if you remember, logarithmic functions are inverses of exponential functions. So ln x is the inverse of e to the x, because ln x, remember, is the exact same thing as log base e of x. That's what it means. And let me prove to you why ln x is the inverse of e to the x. Just in case you don't remember how, I'll do it algebraically off to the side quickly for you. So we have the function y equals e to the x. If I want the inverse of that, inverse functions have their x and y coordinates switched, so algebraically I can just switch x and y, and then rearrange this to isolate for y. I could do that by, I could take ln of both sides, and then use the power rule to rewrite the exponent of that argument as the coefficient of the log. And then remember, ln e is just 1. So on the right side, I have y times 1, which is just y. So I have y equals ln x. So that's the inverse function. Ln x is the inverse of e to the x. And for inverse functions, all we have to do is swap their x and y coordinates. So if negative 1.37 is on the graph of e to the x, that means 0.37, negative 1, is on the graph of ln x. And if 0, 1 is on the graph of e to the x, that means 1, 0 is on the graph of ln x, and so on. And this function, ln x, it doesn't have a horizontal asymptote at y equals 0. It has the opposite of that. It has a vertical asymptote at x equals 0. So let me draw that function on this graph as well. So here's a rough sketch of what the ln x function looks like. And graphically, I don't know if you remember, but inverse functions are diagonal reflections across the line y equals x. And here's the line y equals x. Notice e to the x and ln x are just reflections across that line. Before we get into derivative rules involving exponential functions, let me just do a quick application question about an exponential function that involves Euler's number. Example 2 says the population of a bacterial culture as a function of time is given by the equation p at t equals 200 times e to the power of 0.094 t, where p is the population after t days. It says what's the initial population of the bacterial culture? Well, that just means when time is 0, what's the population? So let's evaluate p at 0. P at 0 equals 200 times e to the 0.094 times 0. Well, that means 200 times e to the 0, and e to the 0 is 1, so we have 200 times 1, which is 200. So the population starts at 200. Estimate the population after 3 days. So we just want to evaluate p at 3. I just put this example in here just to make sure you take the time to find the button for Euler's number on your calculator. So we would evaluate 200 times e to the 0.094 times 3. And now we can just evaluate this on our calculator and we'll get an approximate value for this. So 200 times e to the power of 0.094 times 3. And it's about 265.2. So it's about 265.2. Part C says, how long will the bacterial culture take to double its population? Well, let me rewrite the original function here. So we know the initial population was 200. We solved for that in part A. We want to know how long until it doubles its population. So basically it's saying how long until the population gets to 400. So we'll set the population to 400 and solve for t. My first step in this solution would be to divide both sides by 200. And that would give me 2 equals this power of e. And now since my unknown is in the exponent, if I convert this equation into logarithmic form, I'll be able to easily solve for that exponent. So in logarithmic form, this would become log base e of 2 equals the exponent. And hopefully at this point in your math career, you understand how to convert from exponential to logarithmic. A log function, its job is to figure out what exponent goes on the base, e, to get the argument 2. So the answer to the log, 0.094t, tells us the exponent that goes on e to get 2. And that's exactly where this equation came from. 0.094t is the exponent on e that makes it equal 2. So these two lines mean the exact same thing. And now that we have it in this format, well, we would actually never write log base e. Log base e is the natural logarithm. So instead of writing log base e, I could just write ln for natural logarithm and not have to write a base. Now we know that the base of that log is e. And to isolate t, my last step would just be to divide both sides of the equation by 0.094. So t equals ln 2 divided by 0.094. And I'll get an approximate value for this. T is about, let's do ln 2. So make sure you find the ln button on your calculator. It should be right around your log button. So ln 2 divided by 0.094. I get about 7.37. And what units are we in for this question? It says that t is the number of days. So 7.37 days, that's how long it takes to double. It doubles once every 7.37 days. Notice the original function had a base e power. So we took the initial population of 200 and multiplied it by Euler's number, 0.094 t times. But this function doesn't have to be modeled with a base e power. Part D says rewrite the function as a base 2 power. So if I want to rewrite it as a base 2 power, I just take my population, still started at 200, but instead of multiplying it by e, I'm going to multiply it by 2. Then the exponent on 2, well, how often does the initial population of 200 get doubled? It gets doubled once every 7.37 days. So it would have to be multiplied by 2, t over 7.37 times. Do your total time divided by the time it takes to double once, and that'll tell you how many times it needs to be doubled. And over here in this box, there's just a general formula for exponential growth where the base of the power is 2. The exponent is total time divided by the doubling period, which in our case is 7.37 days. So our original function, 200 times e to the 0.094t, and this function, 200 times 2 to the t over 7.37, those are two equations that model the same function, or at least really close to the same, because that 7.37 is a rounded value. All right, now that we've reviewed what Euler's number is, you've learned what the natural logarithm is, I think you guys are ready to differentiate some exponential functions. So I know I have an exponential function if the exponent of a power is my variable x. So if we have an exponential function, b to the x, where b is some number greater than 0, I can differentiate it by doing the exponential function b to the x multiplied by ln b. So how do I find the derivative of this exponential function, y equals 2 to the x? I find the derivative, which I'll denote as y prime, by doing the exponential function, 2 to the x, multiplied by ln of its base, so ln of 2. That's its derivative. Let's try another one, part b, and this is a great one. If I want to differentiate e to the x, well, e, remember, is just Euler's number. It's that irrational number, 2.718, so on. Its derivative would be equal to e to the x times ln of the base of the power, so times ln e. And what's ln e? Well, that means what exponent goes on e to get e? That's 1. So the derivative is e to the x times 1, which is just e to the x. So the derivative of e to the x is e to the x. Isn't that kind of cool? The y values of the e to the x function actually also tell you its own slope. So the function tells its own slope. Kind of a cool thing to think about. Part c. I'll just need to use the constant multiple rule here. If I want to differentiate 3 multiplied by this exponential function, the derivative of that would just be equal to 3 multiplied by the derivative of 2 to the x. And the derivative of 2 to the x is 2 to the x ln of the base. And there's nothing I could simplify there. I just have 3 times 2 to the x times ln 2. Part d, I'll just have to use my sum rule for derivatives. I want to differentiate a sum of two things. So I can find the derivative of that by just finding the derivative of 3 to the x plus the derivative of 1. And the derivative of 3 to the x is 3 to the x times ln of the base plus the derivative of 1 is 0. So I don't have to write plus 0. There's my derivative. Oh, and I just put a slide in here just to really make sure you notice that the derivative of e to the x is e to the x. That's going to be really important as we move forward in this unit. Example 4 says, find the equation of the line that is tangent to the curve y equals 2 times e to the x at x equals ln 3. So let me just show you in Desmos what we want. Okay, so I have the curve 2 times e to the x drawn. And what I want to do is find the equation of the tangent line that touches that curve at the point where x equals ln 3. So I want the equation of this purple tangent line that you see here. Now, if I want the equation of that tangent line, I'm going to need to know its slope. And remember, the tangent line represents the slope of the original function at that point, and I can find that by using the derivative of the original function. And I'm also going to need to know the y-intercept of this line, which I could get by plugging in a point that's on the line, so this point right here, which it shares with the original function, and the slope of the line, which I get from the derivative, and then solve for b. Let me start by finding the slope of that tangent line. And I can find the slope of that tangent line from the derivative of the original function. So when I differentiate 2 times e to the x, the constant multiple rule tells me just do 2 multiplied by the derivative of e to the x. And the derivative of e to the x is e to the x ln e. But ln e is just 1, so I don't need to write it. It's 2 times e to the x times 1, which is just 2 times e to the x, right? The derivative of e to the x is just e to the x. So my derivative of 2 times e to the x is 2 times e to the x. And now I want to use this function to find the slope of my original function at an x value of ln 3. So into the derivative, let's plug in ln 3 for x. So I'd have 2 times e to the power of ln 3. And e to the power of ln 3, well, that's just 3. So I have 2 times 3, which is 6. So my slope, I'll call m, is 6. That's the slope of my tangent line. And you might be saying, well, hold on, why is e to the power of ln 3, why is that just 3? Well, hopefully you remember the rule b to the power of log base b of a, that's just equal to a. Because what's this really asking? The exponent is a logarithm, and that logarithm evaluates what exponent goes on b to get a. So what happens if we put that exponent on b? We, of course, get a. And if you want some easy numbers to help you understand that, like let's say we had 3 to the power of log base 3 of 9. Well, of course, that's going to equal 9. Why? Well, log base 3 of 9 means what exponent goes on 3 to get 9? And that answer is 2. So what happens if we put 2 on 3? 3 squared is 9. So for that reasoning, e to the power of ln of 3 is 3. Because remember, ln is just log base e. Okay, now we need a point on the tangent line. And to find a point on the tangent line, we find the point that the tangent line shares with the original function. So I know the tangent line touches the original function when x is ln 3. So plug ln 3 into the original function, and we'll get the y-coordinate of the point. And remember, the original function is actually the same as the derivative. So when I plug ln 3 into the original function, I'll get the same answer as when I plugged it into the derivative. I'll have 2 times e to the ln 3, which we discovered before was 2 times 3, which is 6. So the point the tangent line shares with the original function is the point ln 3, 6. And now I can use this information to write the equation of the tangent line. I have an xy point, I have the slope, I could solve for b. So I'll sub in what I know. Y is 6, m is 6, and x is ln 3. Therefore, an exact value for b would be 6 minus 6 ln 3. So my final equation would be y equals 6x plus 6 minus 6 ln 3. Example 5, let's do an application question where we need derivatives of an exponential function. A biologist is studying the increase in the population of a particular insect in a provincial park. The population triples every week. Assume the population continues to increase at this rate. Initially, there are 100 insects. Determine the number of insects present after 4 weeks. So we have to start by writing a function that'll tell us the population of insects at any time we want. And my variable for time, I'll let it stand for the number of weeks, since that seems to be what it's telling us about in the question. So my population, based on time, well, the population starts at 100, and it's tripling once every week. And I'll let t stand for the number of weeks. If I wanted t to stand for number of days, my exponent would then have to become t over 7, because it would triple once every 7 days. But since it triples once every week, and t is number of weeks, my exponent would be t over 1, which is just t. And I want to determine the number of insects after 4 weeks. So p at 4 equals 100 times 3 to the 4. That initial population of 100 is going to triple 4 times. So let's let our calculator evaluate that for us. I need to triple 100 4 times. And that gives me a population of 8,100. Part B says, how fast is the number of insects increasing? Part 1, when they are initially discovered, and Part 2, at the end of 4 weeks. Since it wants to know how fast is the number of insects increasing, that's asking for the rate of change of insects with respect to time. And that's exactly what the derivative would tell us. It'll tell us the rate of change at any one point. So we'll use the derivative to answer part 1 and part 2. So I'm going to need to find the derivative of my population equation. So let me start by rewriting the population equation. P at t equals 100 times 3 to the power of t. And let me differentiate this. P prime at t equals, the derivative of 100 times 3 to the t would be equal to 100 times the derivative of 3 to the t. And the derivative of 3 to the t is 3 to the t times the ln of the base. so times ln 3. And in part 1, I want to know what is the rate of change of population with respect to time when they're initially discovered, so that means when time is 0. And part 2 wants to know at the end of 4 weeks, so I'll need p prime at 4 for part 2. So the rate of change when they're initially discovered, so when time is 0, I'd have to plug in 0 for t. And let me evaluate this on my calculator over here. So I have 100 times 3 to the 0, and 3 to the 0 is just 1, but I'll type 3 to the 0 anyway, times ln 3. And I get 109.9. So p prime at 0 is 109.9. And remember, this will give us the rate of change of y with respect to x, and in this case that means it's the rate of change of population with respect to time. So it's 109.9, and it's population of insects, I should say. So 109.9 insects, and I believe our time was in weeks, so insects per week. So that means the amount of insects when they're initially discovered is increasing at that rate. It's increasing at a rate of 109.9 insects per week. How about at the end of 4 weeks? At what rate are the insects increasing? So I would do 100 times 3 to the 4 ln 3. And let me evaluate that. We get about 8,898.8 insects per week. So those are my 2 rates of change. Those are how fast the number of insects are increasing with respect to time at those 2 exact moments in time. All right, that's the end of this lesson. Make sure you give the practice questions a try.